Quick derivatives. I want to find the first derivative and the second derivative. So first derivative is going to be 10x plus 3. The second derivative is going to be just 10. Number 2, I can do this rapidly. I know off the top of my head how to do this. It's just going to be 1 over 2 square root x. It's a little pattern, but I'm going to derive that for you. So if that's the square root of x to the first, I can rewrite that as x to the 1/2. And now I'm going to implement the general power rule. And the derivative would be y prime equals 1/2 x. And don't forget you have to subtract 1. I write it as 2 over 2. That would give me negative 1/2. No negative exponent, so y prime is going to continue to equal 1 over 2 x to the 1/2. And I rewrite x to the 1/2 in radical form, so my final answer is going to be y prime equals 1 over 2 square root x. There is a shortcut for doing the cube root of x squared or the cube root of x, but I'm going to go ahead and plug through and do this the long way. I'm going to rewrite this in exponential form. That's going to give me y equals x to the 2/3. Cute little way to remember it is what's in the bucket goes on the bottom. Now I'm going to take the derivative. I'm going to apply the general power rule and do 2/3 times the x, so that's going to give me 2/3 x. Don't forget I'm supposed to subtract 1, so I'm going to write 1 as 3 over 3. That's going to give me negative 1/3. Now I don't want to write the negative exponent, so I'm going to send him down and change the exponent to a positive, and the cube root to the 1/3 is a cube root. So the final answer is going to be 2 over 3 cube root x to the first. Now we start to do product rule. And the product rule is this, u dv plus v du. I'm going to break this in half and call this front x cubed u and this back sine x v. So u equals x cubed, v equals sine x. The derivative of u is 3x squared. The derivative of v, the derivative of sine x, is cosine x. Now here it comes, this is kind of cute. I have u dv, u times v, derivative of v. So that's going to give me just x cubed times cosine x. Now I have to do plus v du. That's sine x times 3x squared. But when we write these down, we usually put this first. I don't want to say duv, but it's v du. But by the commutative property, I'm allowed to put the 3x squared first. Times sine x. Chain rule problem. I'm going to actually do a big derivative and then a little derivative. So the derivative is going to be 7 times 3, 21, times the quantity x cubed plus 5. Then I have to subtract 1 from that to the 6th. But now I have to take the derivative of the inside. And the derivative of x cubed plus 5 is 3x squared. And we have to simplify a little bit. We have to write that out in front. So that's going to be 63x squared times x cubed plus 5 to the 6th. Number 6, another chain rule. The derivative of cosine is negative sine. Then I just write that down, 5x squared minus 8. But the chain rule says I have to now take the derivative of that. The derivative of 5x squared minus 8 is 10x. And I'm going to write it out front. So it has to be negative 10x. I just wrote it out front. Another chain rule problem. The derivative of tangent is secant squared. Copy this down, 3x squared minus 4. But now I have to take the derivative of the guts, which is 6x. And I'd like to put that out front. Quotient rule. Cute little way to remember the quotient rule is low, d high, minus high, d low, over the denominator squared, it must go. So the high is the top, the numerator, which is x minus 7. The low is the denominator, which is x plus 1. The derivative of the high is just 1. The derivative of the low is just 1. Now I'm going to do my little dance. Low, d high. So that's going to give me x plus 1. Minus high, d low. That's going to give me x minus 7. But don't forget, you have to quantify that because you're subtracting the whole item. All over the denominator squared, it must go. So the denominator is x plus 1. If you want to, you can spruce this up. X minus x eliminates. And then 1 minus 7. So my final answer would be 8 over x plus 1, the quantity squared. Now, we have a product rule and a chain rule. Product rule and a chain rule. Product rule is u dv plus v du. I'm going to set up my u equals, my v equals, my du equals, and my dv equals. My u is the front part, which is e to the sine x. My v is the back part, which is just tan x. The derivative of e to the sine x is e to the sine x times the derivative of the guts, which is actually going to be cosine x. The derivative of tangent x is secant squared x. Now I'm going to implement the product rule. u dv plus v du. u dv. So that's going to give me e to the sine x times secant squared x plus v du. Tangent x times cosine x e to the sine x. I'd like to say we can leave it there, and a lot of us would like to. If it were extended or free response, go ahead and leave it. But if it's multiple choice, the multiple choice solutions won't look anything like that. Isn't tan x really sine over cosine x? So can't the cosines eliminate? Not leave me a sine x? Now, I'm going to take this and factor that out also. So my final simplified answer will look like this. E to the sine x, parentheses, secant squared x, plus sine x. And I think that's about as far as we go with that. It's asking me to expand this and write it in polynomial form. I can see right away that that's going to be x squared minus 1. And then I'm going to FOIL this, x minus 2 and x minus 3, and that's going to give me a trinomial x squared. Minus 2x minus 3x would be minus 5x. And then negative 2 times negative 3 would be positive 6. I have to further expand this. I'm going to use a Punnett just to organize my data a little bit better. So the x squared minus 1 and the x squared minus 5x plus 6. X squared times x squared is x to the fourth. X squared, that's negative 5x cubed times 6x squared. Negative x squared, positive 5x minus 6. So my expansion is going to be x to the fourth. Whoops. Minus 5x cubed. I have to combine these. Plus 5x squared. Plus 5x minus 6. From that, I want to find the derivative. So the derivative of this is going to be 4x cubed minus 15x squared plus 10x plus 5. And then the derivative of that is going to be 12x squared minus 30x plus 10. Now it's asking me to graph y, y prime, and y double prime. To graph the original equation, y, just by looking at its factors. This means it's going to go through positive 2 on the x-axis. This means it's going to go through negative 1 and positive 1. Negative 1 and positive 1 on the x-axis. And this here means it's going to go through positive 3 on the x-axis. And notice the general shape. It's also going to go through negative 6. That's the y-intercept. 1, 2, 3, 4, 5, 6. So, I don't know, it's going to look kind of like a big W. I don't know how deep down this one goes. So I'm going to go ahead and just say it looks like that. I'm not certain. I'm just going to take a guess. And now I'm going to go ahead and use my calculator to graph the original. You want to go to y equals, and you want to type in either the original function or your expanded function. I'm going to type in the original function, just so you can see that you don't have to do the actual algebraic manipulation to get the equation of the graph. So it starts off parentheses, x minus 2, parentheses, x plus 1. I'm going to go ahead and type that in. Just like it looks. And then I'm going to go ahead and graph that. But before I do, I'm going to clear this out so you can see what I'm going to do. And I hope this graph matches sort of my graph over here. And yes, it does. Not exact, you know, but I just did a rough sketch. I do know that this is going to be a minimum. I do know that this is going to be a local max. And I do know that this is going to be a local minimum. Okay, relative min, relative max, relative min. It's x to the fourth, 2 bumps. Now I'm going to show you how I can graph the derivative without having to evaluate it. I'm going to graph the derivative of this curve. What you want to do is hit math. And notice, 8 is the derivative, math 8. And it gives you this dd something. And that's ddx. ddx of, and now here's the trick. I need to put my first equation, y1, in there. And the keystroke to get that is going to be alpha calc. And it brings up this table. And notice, that's y1. So I'm going to do alpha calc of y1, which is just 1. And there it is. It put the y1 in there for me. Pretty nice. And now I want to evaluate it for all x. And now I'm going to hit graph. And it takes a little while. It takes a little while, but it will graph it for you. It will graph it for you. You can see it's thinking up here. And there it is. Notice, the original graph has 3 humps. The derivative has 2 bumps. 2 bumps. So I'm going to go ahead and graph that. Goes a little bit inside of 1. Goes through here at positive 5. 1, 2, 3, 4, 5. Continues up a little. And then goes through between these 2. So it's going to come up, go through, goes up a little. Goes through, goes up a little through 5. Comes down. And notice, right here it goes through again. And now it's going to turn and go up between these 2. And go on forever. Now, I gotta be honest with you, this is going to start to look very busy. I'm going to graph the second derivative now. And I already have it in, but so you can see it happen, I'm going to clear it out. I'm going to hit math 8. And that gives me the derivative. Now I'm going to enter ddx, so I put an x there. Now I need y2 in there, y2. So it's going to be alpha calc. And I'm going to type in a 2 for alpha 2. At x, for x equals x for all x values. And now I'm going to hit graph. And it's going to graph the second derivative as well. It takes a while. It takes a while. Second derivative will only have 1 bump. And notice, it goes between 0 and 1, right there. And then it comes back up and goes through a little bit to the right of that coordinate. A little bit to the right of that coordinate. And I'm going to graph that on my graph paper. So it goes down through between 0 and 1. 0 and 1. I don't have the exact go-through point, but the y-intercept is going to be at plus 10. So way off the graph, comes down. Has a minimum way down here below. And then goes through between, almost right through that spot. And yes, it's a very busy graph. Very busy graph. But you can graph it quickly. First entering the function in unfactored form, then using the math 8, and it'll plot those, and graph it for you pretty rapidly. Let's travel on planet Earth in a parabolic curve. What I want to do is write the position function for each situation. A ball is kicked from a 3 foot off the ground with an initial velocity of 64 feet per second. The drawing of that is going to be this. It's kicked from 3 feet off the ground. So 1, 2, 3 is where it's going to start. Then it's going to rise up from that point and then parabolically fall down. And at a certain point in time, it's going to hit the ground. This is t equals 0. This is how long it takes for it to ground. And somewhere along here, it's going to reach a maximum. And that's going to be the vertex of the parabola. Now, every object on planet Earth, in English terms, falls at a rate of negative 16 feet per second. So we're going to use that. A ball is kicked from 3 feet off the ground with an initial velocity of 64 feet per second. So here comes the position function. It's going to start off with negative 16 t squared. Then I use the 64 plus 64 t. Then I add the 3 feet where it started, plus 3. Now I need to do to find the velocity function is take the derivative of the position function. 2 times negative 16 is negative 32, t plus 64. Now, to find the acceleration function, all I need to do is take the derivative of the velocity function. So that's going to give me negative 32, and that's it. A golf ball is hit with an initial velocity of 96 feet per second. The original position function is going to start at negative 16 t squared. Now, it gives me the initial velocity, so it's plus 96 t. And now, it tells me it's hit. A golf ball is hit with if it's a golf ball, it's hit off the ground. So the picture is going to look like this. It's hit off the ground at 0, 0. So this is going to be plus 0, but we don't need to put that there for the initial height. To find the velocity function, you just take the derivative of that. So that's going to give me negative 32 t. And to find the acceleration function, you just take the derivative of that. And that's going to give me negative 32. This here's position. It would be in feet. This one here's velocity. It would be feet per second. And this is acceleration, which is feet per second squared. A KDR brother falls from a 256-foot trestle. So imagine you're walking on a train track, and you're standing up here, and you fall. It's going to start off with negative 16 t squared. Now, what's the initial velocity? He's falling, he's dropping. He isn't jumping down or jumping up, so there's no initial velocity. So it's going to be plus 0 t, but you don't need to put that. And now, how high is he when he starts to fall? Plus 256. Now, to find the velocity function, all I do is take the derivative. So it's going to be negative 32 t. Notice this goes to 0. And then the acceleration function is going to be negative 32. Again, this is position, so it's just in feet. How many feet it's traveled over a given amount of time. This here is going to be feet per second. And acceleration is feet per second squared.